Good morning, everyone. Welcome to our Friday seminar. It is my pleasure to introduce to you our speaker today, Dr. Runmin Wang from the Southern Methodist University. Runmin is an assistant professor at SMU in the Department of Statistical Sciences, where he joined in 2020 after receiving his PhD. So he received his PhD in statistics from UIUC, which I believe is reasonably well represented in the audience as well. And he was advised by Dr. Xiaofeng Zhao there. And before that, he also received his master's, also from UIUC in statistics in 2015. And he got his bachelor's in statistics and operations research from the Hong Kong Baptist University in 2013. His research interests are mainly in change point analysis, high dimensional inference, time series analysis, and also non-parametric methods and their applications in econometrics. And today he has done some very good work, by the way, first of all, in all these areas, some of which have already appeared in good journals, including JASA journals. And today he's going to tell us about some of his recent interesting work on statistical inference or change points in high dimensional settings. So please join me in welcoming him.
Good morning, everyone. It is my great pleasure to present some of my recent work here. The one I'm going to talk about today is the statistical inference for change points in high-dimensional data. So I know there are many experts here in the audience, but I'm still going to talk about the definition of the change point problem first. So what is a change point? So usually we assume some homogeneity assumptions over the time for the data, for example, the ID assumption. But sometimes this assumption can be not realistic or even violated in real world. So one type of heterogeneity is that you have, say, a sequence of ID data, and then the distribution suddenly change at a certain point and just change to another distribution. So we call this point is a change point. So there are usually two types of questions related to change point. The first one is the existence of the change point. Then the second one is the estimation of the change point. Where are those change points, right? So to answer these two questions, usually you need a complete data records. And this is also called the offline approach or the retrospective study. There's another type of problem, so-called online monitoring. Basically, you have sequentially arrived data, and you would like to signal an alarm for the change point at the earliest possible time, but also control the typo error. In today's talk, I'm going to focus on the retrospective study. Basically, we have the complete data records, but we have certain extensions to the adaptive setting as well in our paper. So as you can see, there are many applications in real world. For example, finance, neuroscience, speech recognition, or credit card, a credit card fraud detection, among many others. But now I'm going to use a genomic data to illustrate what is a change point problem here. So let's think about the CGH data. This CGH is a technique that allows the detection of chromosomal copy number abnormality by comparing the fluorescence intensity levels from the patient of the DNA fragments from the patient to a reference sample. So in this data set, we collect 26 patients, and for each patient, we have 200 locus. So the sample size would be 200, and the dimensionality would be 26. And for a normal person, the sequence should be a stationary sequence around 0. But for patients, we observe there are some abnormality regions here. Some of the abnormality regions are only shared across a given patient. Some of them are shared across many different patients simultaneously, and we call this as a dense change. We believe that this dense change can be more likely to be disease-related because that is actually shared by many different patients at the same time. But in any case, we can use change point detection technique to locate the boundary of those abnormality regions. Right? Those are the change points. Today, we're going to talk about high-dimensional problems where P, the dimensionality, can be greater than the sample size N. This is definitely not a high-dimensional problem because P is only 26. But as you collect more and more data, eventually, we believe that there's a potential that the problem can become to a high-dimensional problem. So this is an illustration of the change point problem in reality using the genomic data. So in today's talk, we're going to talk about two problems. The first part, the testing problem. The second part, estimation problem. One, answer the existence. One, give you the solution to the locations. So I'm going to talk about the testing part first. So here, let's consider in the simplest setting, where we have at most one change point in the mu vector of a high-dimensional time series, a high-dimensional data sequence. So we consider, in the paper, we extended further to multiple change points with dependent data. But for now, since because of the time, I just want to focus on the simplest setting to give you some flavor about the method and also the cornerstone of the whole story. So I'm stick to the single mean changing point model here. So the data generated RID from this model with this overall mean vector mu and vector of the mean change delta. The symptotic framework here we are talking about is that both n and p can go to infinity, okay, which is a high dimensional setting. And all these parameters are unknown. This K0 is the changing point location, okay, potential changing point location. Under the null hypothesis, if there's no changing point, then delta would be a zero vector, right? Under the alternative, delta would be non-zero. We know there's at least one changing point. So now we can formulate the existent problem to a hypothesis testing problem. Some of you may think this IID assumption may be quite restrictive for changing point problems, especially if you have data from finance or economics. But in fact, this is a commonly assumed assumption in modeling changing points in genomic data. Also, as we said before, we have extensions to dependent data in the paper. So if time permits, I'm going to talk about the extensions to dependent data at the end of the talk. But for now, let's just stick to the IID setting here. So this is our DGP. And in the current literature, so as we illustrated in previous real data example, you see that there are two types of changes, depending on the sparsity of data. If the change is shared across many different patients, that's a so-called dense change, right? People usually use the L2 norm of delta as the parameter, right? If this change is only specific to one individual, say this delta is a sparse vector, then people usually use L infinity of delta as the parameter in interest, right? That is very reasonable. Certainly, there are some methods that try to combine L infinity based method and L2 based method to achieve some adaptive inference, which has decent power against both dense and sparse alternatives. Especially, I'm going to mention the last one. This is a direct extension of the method we're going to talk about today. Basically, the idea is we formulate tests for different LQ norm of delta for different Qs. When Q is large, we know the power would be better for sparse alternatives. And when Q is small, we're going to have better power against the dense alternatives. So we just combine, different tests for different LQ norms, as simple as Povorani, for example. But in the current literature, you can see there are usually many restrictive assumptions. For example, some of them may require that the dimensionality can be smaller, at most polynomial rate, for example. Some of them may require some distributional assumption. Some of them may have cross-sectional independence, or some of them may really have tuning parameters here. So our goal is to try to get rid of all these restrictions by developing a new method here. So here are some highlights of our method. So first, our method is targeting at the dense alternative. So in other words, our method is based on the L2 norm of delta, all right? Then we are fully non-parametric. There's no distributional assumption. We have no tuning parameter. And we can allow the extension to temporally dependent data and adaptive testing, okay? Specifically, reason for dense alternative, well, think about the CGH data we talked about before. We believe that dense changes can be more likely to be disease-related. Or think about if there are some economics or political events that can actually affect the volatility of many stock returns at the same time. Think about financial crisis, right? Usually, multiple stocks are affected at the same time. These are all dense change. Okay, so how do we construct our test statistic? Well, if you think about an infeasible case, where the changing point location K0 is known, then essentially we are comparing the mean vector for the pre-break sample and the mean vector for the post-break sample, right? So the problem is reduced to a two-sample mean testing problem in high dimension. And this has been well studied in recent years in many literature. For example, in this Chen and Qin's paper, they consider a U statistic formulation. How to construct the U statistic? You pick one observation from the pre-break sample. You pick one observation from the post-break sample, okay? Then the difference between those two would be, the expectation would be delta, right? You pick another one from the pre-break, you pick another one from the post-break, the expectation of the difference would be another delta. Because of independence, the expectation of the inner product between those two differences would be delta transpose delta, which is the square L2 norm. That is exactly the parameter we're interested in. So we do the same thing for all possible tuples with observations with distinct indices, two from the pre-break, two from the post-break, and we take the average of all those inner products, and we are obtaining a so-called U statistic. It's unbiased and with minimal variance. Under the null hypothesis, there's no delta, so the expectation would be 0 for all k's. Right? Under the alternative, although we don't know where is our k0, but if you calculate the soup over all possible expectations, at least at k equals to k0, you have this positive expectation, right? Because at that point, delta is non-zero, so the expectation is positive, right? So this reminds us that the soup of G and K can be considered as a very good test statistic. And in fact, that works. So we just illustrate using this toy example. We generated data IID from multivariate normal, n equals to p equals to 50, and the chaining point happens at the middle of the sample, that is 25. So you see this soup of G and K is indeed very large under the alternative. On the other hand, the maximizer of this G and K is very close to the true chaining point location. So this indicates that the maximizer of G and K can be considered as a location estimator, right? And indeed, this is what we have done in the paper in the second part. I'm going to talk about this estimation later, but for now, just keep in mind this U statistic is very related to our chaining point problem. Okay. Then we need to derive the limiting null distribution for the soup of G and K. These are some current results in the literature. Under certain conditions with proper normalization, this G and K converges in distribution to standard normal for every fixed K. Okay, but this is not enough because we need the result for the soup of G and K. So we have to have a process level convergence by treating this G and K as a stochastic process in K. But this is so-called finite dimensional convergence, which is weaker than the result we need. So we have to develop some stronger result, which is a process level convergence. On the other hand, if you take a look at this normalizing constant here, these quantities are known, the Frobenius norm of sigma. Well, we can ratio consistently estimate it under the single mean chaining point model with independent data. But if you want to do something more, say multiple chaining points for dependent data, there's no way to get ratio consistent estimator, at least for now. But in the paper, we would like to provide a unified treatment for all these situations. So we don't want to really use a plug-in estimator for the simplest setting. So we have to find a way to get rid of the direct estimation of this nuisance parameter. And this reminds us the technique called self-normalization here. What is self-normalization? It has a very long history, which can be even dated back to 1908. The well-known William Gosset used a student P statistic. And Xiao in 2010 extended that to a general time series inference for multivariate data. And Xiao and Zhang here means Xianyang, further extended here to a chaining point problem in low dimension in 2010 for the first time. But what is exactly self-normalization? Let's take a look at a simple example. That is an inference problem for a strictly stationary time series, p-dimensional, p is fixed. Say we want to test for mu or construct some confidence set for mu. Most of the time, under the certain regularity conditions, CLT holds, and you have to consistently estimate this unknown long-run variance matrix gamma. Well, people can use some like window estimators to consistently estimate that, but that usually involves a selection of the bandwidth and the selection of the kernel function. So different people may use different kernel functions or different bandwidth so that they have different results. How to solve that? Well, Lobato and Kiefer et al., they independently consider to use this self-normalizer, which is an inconsistent estimator of this gamma. Okay? By using this, if we also have this invariance principal holds, then this what type statistic converges in distribution to this UP, which is just a functional of the p-dimensional standard Brownian motion. As being said, it is pivotal, so you can simulate the quantiles if you can simulate p-dimensional Brownian motion. All of us can. And you do not need to estimate this gamma anymore, because all the numerators here and denominator, they are proportional to this gamma. So it has got canceled out from both sides in the limit. We just don't need to estimate that anymore. Okay? And in fact, we can do more than just a mean vector. So we can do that for a general parameter by constructing the recursive statistic using the plug-in estimator based on the first T observations. And we can construct this Wn, the self-normalizer, and we get the self-normalized statistic, and the limiting distribution would be UP. But unfortunately, we cannot directly use that for our chain point problem because we are talking about high dimension setting. This framework is not theoretically justified under large P small n case. And it is not even not applicable when P is larger than n because this Wn may not be even invertible. So we have to have a way for our chain point problem, but we can still adopt that idea by constructing some recursive statistic. Basically, this is the numerator of the U statistic calculated based on the L subsample from XL to XM with the potential chain point in K. Then we calculate our self-normalizer accordingly. It contains two parts, one for the pre-break data, one for the post-break data. And we do this because this gives us a better power behavior. This is not a new idea. It was first introduced in Shaw and John's paper in 2010, but for low-dimensional chain point problem. And finally, we have our self-normalized statistic. This Tn is our test statistic. Okay, we do not need to estimate the nuisance parameter anymore. Okay. Then the next step would be deriving some limiting null distribution for this Tn, right? We'll take a closer look at this test statistic. This Tn is just a continuous functional of this Vn process, right? And by some mathematical simplification, this Vn is actually a continuous functional of this Sn process, which is a two-parameter process. So by continuous magnitude theorem, if you can obtain the limiting null distribution for Sn, you automatically get the limiting null distribution for Tn by the function of continuous mapping. So now the goal is how to derive the limiting null distribution for this Sn. We have to have certain conditions. The first condition is a commonly assumed assumption in many two-sample mean testing problems in high dimension. The second one is a new assumption based on so-called joint cumulants of the components in the innovations here. But those two assumptions are essentially telling us the cross-sectional dependence cannot be too strong. We have weak cross-sectional dependence. Many commonly assumed current structure can satisfy. For example, identity sigma, AR1 type, banded. One counterexample is called compound symmetric, where we have all the off-diagonal elements are the same, constant, and non-zero. In that case, that indicates a very strong component-wise dependence. It cannot satisfy our two assumptions. On the other hand, we do not have any restriction on the order of P. So P can go to infinity freely, all right, even at the exponential rate of n. Under those two assumptions, with this normalizing constant, Sn process converges in distribution process level to this Q process for any A and B between 0 and 1, A smaller than B. And this is just nothing but a Gaussian process with this covariance structure. It is pivotal. So by continuous mapping theorem, we get the limited null distribution for Tn. Although it looks like quite complicated, but if you can simulate Q process, you can obtain the critical values for this T distribution. Okay, it's pivotal. So now the goal is how to simulate this Q. Well, this Q is nothing but a Gaussian process. And all of us know how to simulate a standard Brownian motion, right? Where we just take standardized sum over ID, standard normal random variables, and we get Brownian motion. And here we are doing the same thing. We construct a 2D array that contains ID standard normal. For any A and B, we take the standardized sum over the sub-square matrix from row NA to row NB, column NA to column NB. This is approximation for QAB process. So it's just a 2D generalization of the standard Brownian motion, right? You can use each row or column to approximate standard Brownian motion. Now we just take the sum over the sub-square matrix. So it can be simulated very efficiently and very quickly in reality, so we can obtain the critical values for the T distribution as well. And here's the histogram. We rejected the null hypothesis when the test statistic is greater than the critical value. Okay? So it's very easy to use. There's no parameter, there's no tuning parameter at all. You do not need to estimate any nuisance parameter here. Okay? These are behaviors under the null hypothesis. Under the alternative, depending on the signal strength, we have different behaviors. If the signal is too strong, the test statistic converges into to infinity, the power would be eventually 1. Okay, the test is consistent. When the signal is weak, the limiting distribution would be the same as the limiting null. Then we have trivial power. And then the signal to noise ratio is at moderate rate. We have non-trivial power. The limiting distribution would be a non-centered version of this T distribution. I want to talk about a special case where the sigma is identity. Okay. If this sigma is identity, then this local alternative is reduced to this rate. If we further impose a dense structure for this delta, where all the components in delta are the same, then the magnitude for each component is reduced to this rate. This is a very weak signal that cannot be detectable for any L infinity based method. Okay? Because our method is aggregating over all components. So we take the squared sum over all components. Even each element is small, when P is large, the overall signal is strong. But L infinity based method just look at the maximum value of the delta. So overall level would still be small if you have very small magnitude for each element. So overall, L infinity based methods are powerful for sparse and strong signal. L2 based methods are powerful for dense but weak signal. For dense and strong, everyone can do that, right? So let's see some simulation studies here. We just get a bunch of N and P, and we simulate the data from normal distribution. We have 4 choices for the structure for sigma. Keep in mind, the compound symmetric case does not, the compound symmetric case does not satisfy our assumption. So you may expect some poor result for that setting. We have 2 levels of the alternatives, and we repeat the simulation 5,000 times. Okay. We compare our method with some plug-in estimation. Remember, we say for simple mean chain point model with only one chain point, we can have plug-in estimators, right? So we just adopt some jackknife estimator proposed by Chen and Qin to ratio consistently estimate this norm. For the second one, we use the same estimator, but based on the demeaned data. The third one is an oracle one. We just use the choose for the norm, just for comparison. We also compare our method with some adaptive approach mentioned in this paper, because I don't really know how to pronounce that, the author, so I put as the EH method here, okay? So here are some results. I probably give you some time to read those small tiny fonts here, but essentially, for all settings, EH fails, probably because they have a quite restrictive assumptions, and not all of our setting can satisfy those assumptions. So we will mainly compare our TN with those 3 plug-in estimators. All these estimators are based on the U statistics. Okay. Under the null hypothesis, our self-normalized statistic has a quite accurate size comparing to the other competitors, especially when N is relatively small. Under the alternative, if N is large or signal is strong, our method have power close to 1. When N is small, our method has a little bit advantage over the other competitors, but when A is moderate with mild signal, we observe a little bit power loss here for some comparisons here. This is not surprising because self-normalization is well known for its accurate size, but the trade-off is a slight power loss. For low-dimensional data, this power loss usually is between 20% to 30%, but here the power loss is very mild, sometimes even not noticeable. So overall, our self-normalized statistic is still recommended because of the advantage for high-dimensional data, accurate size with a very mild power loss. These are the results for ID case and AR case. We also have the result for the banded case and the compound symmetric case. If you look at the compound symmetric case, all methods have very serious size distortion. Well, it's not surprising because we know the weak cross-sectional dependence is required for all use statistic-based approach. But in this case, the cross-sectional dependence is too strong. So the limiting null distribution will not be accurate anymore. Okay. So in the paper, we further extend our method to the most general setting, multiple chain points with dependent data. And we also modify the estimator to test the chain points in colored matrices, also estimate different locations together with some segmentation algorithms. But for the sake of time, I'm going to skip these extensions for now and directly jump to the estimation problem for single mean chain point model. That's basically the same DGP we talked about in the first chapter. But before I directly jump to the second part, any questions for now? Great. I guess I have a very clear explanation here. So let's talk about the estimation part. We have basically the same setting, okay? But now we know this delta is a non-zero vector because we know there is a changing point, so we estimate it, right? The parameter we are interested in here is this tau zero. That is not changing point. It's the ratio between the changing point and the sample size. We call it a relative changing point proportion or relative changing point location, and this one is fixed. So we estimate this parameter. This tau zero is the parameter in interest. Okay, definitely the goal of the paper is to estimate this delta. This is tau zero. So we have a point estimator for this tau zero. But we believe that the confidence interval is more informative than the point estimator. So we also want to construct some confidence intervals for this tau zero as well. But this usually requires the knowledge of the limiting distribution for this tau hat. This is a well-studied problem in low dimension, and but if you go to high-dimensional problems, in fact, it's also well-studied in recent years. There are many papers, they propose some location estimators. But if we also want confidence intervals, basically say if we also want limiting distribution to the best of our knowledge, these are the only literature we can find. For dense change, Bai in 2010 proposed this least square estimation. They allow serial dependence, but not cross-sectionally dependence. But charted out for the extended theory to allow both spatial and temporal dependence, and these are the L2-based method. For L-infinity-based method, some people consider to use the Gaussian approximation, but since our method is targeting on the L2 norm of delta, so we mainly compare our method with the least square counterpart. Okay, but now the question is why our method, not least square, right? So let's take a look at their objective function. What they are essentially doing here is calculating the so-called within cluster sum of square by splitting the data right at the changing point location. If you split the data right at the changing point, then for each segment, the mean would be constant. So when you evaluate this within cluster sum of square, just like ANOVA or clustering, whatever grouping method here, very naturally, this objective function would be minimized right at the changing point location. So they just use the minimizer as the location estimator. This is very intuitive, theory well established, computationally very efficient, but only for the case p smaller than n. P can go to infinity, but p must be smaller than n. This becomes one of the major advantages. But charted L proved some theoretical results for high-dimensional problems, but they have to have a lot of restrictive assumptions which make the real dimension, the intrinsic dimension of the problem to be low. So indeed, they are still studying the low-dimensional problem. But what we need is a solution for large p small n case. Why their method fail for high-dimensional case? If you do a breakdown for their objective function, well, a centered version, the first term is a deterministic function of the squared L2 norm of delta. That is the signal function. Okay. The second one is a function related to delta and z because interaction. The last two terms are purely based on the random innovations, and we call it noise. If you take a look at the noise 2 term here, that is a function related to the squared L2 norm of zi's. This term can be huge when p is large, right? At least this order of p, right? For most of the setting, the general setting. And when p is large, this term can even dominate the signal. This makes the whole theory fail. Then the natural idea is there a way that we can get rid of this term? And this reminds us the U statistic. Because in the U statistic, we only have tuples with observations with distinct indices. We do not have any zi transpose zi things in our U statistics. And in fact, this is our method. We use the maximizer of the U statistic here as our location estimator. Here we are using a related version. This weighting is not the U statistic weighting, if you're familiar with that. The reason is this weighting performs a little bit better for finite sample and for the case that the changing point is near the boundary of the data. Asymptotically, they are equivalent. So it's still a U statistic-based approach. The objective function achieves its unique maximum at the truth. And if you do the similar breakdown, we do not have noise 2 term anymore. And we almost keep the same signal level. So we gain efficiency almost for free by using the U statistic. Well, you may think this is a very trivial modification, but in fact, the whole theory would be totally different from the least square counterpart. And this is actually one of the major contributions for our paper as well. We develop a bunch of new inequalities to show the theoretical result, the limiting distribution. Okay, this is our estimator for k, and divided by n would be our estimator for tau. Right? We have to derive the limiting distribution based on certain assumptions. These two are our old friend, right? Because we are still using statistics based, so we have to assume weak cross-sectional dependence. We have two new assumptions here. The third assumption here is to regulating the order of the interaction term to be asymptotically negligible. This is not a must. If the opposite set happens, basically means the signal is quite strong, and in that case, even p is larger than n, our estimator would behave exactly the same as the least square counterpart asymptotically. And the result has already been studied in their paper. So in this talk, I'm just going to focus on a regime that has not been investigated by any paper. The last one is providing a lower bound for the signal to noise ratio. This AN is the rate of convergence for our tau hat. Okay, so we just provide a lower bound to let the signal to be detected. Based on those four assumptions, this is our limiting distribution. If the rate of convergence is slow, the limiting distribution would be the minimizer of a two-sided standard Brownian motion with a triangular drift. Then the rate of convergence is mild. It would be the same limiting now, and the same limiting distribution, but the minimization only taking over the integer set because k hat must be integer. And when the rate of convergence is too fast, there's no limiting distribution for tau hat, and our k hat would be a consistent estimator for k0. Okay. If you compare the rate of convergence here with the one for least square counterpart, R is faster. So we do gain some efficiency. And here are, on the left-hand side is the density plot. On the right-hand side is the plot for the upper tail quantiles. So basically means when tau 0 is close to 0.5, the distribution is more and more concentrated. The variance is getting smaller. And so this basically means when the change point is at the middle of the sample, the change point problem is easier compared to the case that the change point is near the boundary. This coincides with our expectation for sure. But the thing is that the limiting distribution is not pivotal. It depends on tau 0, which we don't really know. Also, there are three different asymptotic regimes, right? How do we select the limiting null when we construct the confidence intervals? So this reminds us that instead of using the asymptotic distribution, we may want to use some confidence, bootstrap confidence intervals. And this is one of the, this is actually the parametric bootstrap confidence interval. To generate bootstrap samples, you have. So you're changing one thinking value and you're playing with rescale time. Yes. So there's a weird discrepancy going on that you're rescaling, and of course now in rescale time what you have is something that you can write on the real line, it's a distribution which is continuous. But you're estimating an integer because in order to find out the change by n and that. So what does it actually mean when you sort of say about the Brownian motion, you sort of confidence interval based on a Brownian motion, or maybe using Bootstrap? Because really what you have to do is sort of take into account that you have integers. Right, that's a very good question. I believe this is probably one of the reasons why this paper cannot be published. But I mean, not really. The reason is we are actually studying some asymptotic behavior here. So more likely it's just like a theoretical side. The n goes to infinity. So the discretization is not that important. All right, but for finite sample, definitely we have a huge room to improve for this project. So I would say that's a very good question. But here we just assume everything happens when n is sufficiently large. Then we can proceed. All right. Okay, so we have this bootstrap confidence interval, and to generate bootstrap samples, you have to have those parameters estimated here. The estimate is k0 by our k hat. We estimate this delta by first estimating the square L2 norm of delta by using U statistic. And here I just assume we have a uniform structure for this delta where all the elements are the same. Okay. To estimate the sigma, we first use the jackknife estimator we used in the previous simulation to estimate the Frobenius norm first. And we assume it has a diagonal structure with equal elements. We use this way to estimate all the parameters, and we generate bootstrap samples IID from normal. And we used bootstrap confidence interval to approximate the true confidence interval, right? Use the Bootstrap distribution to approximate the true distribution. Here you may wonder why we can simply regardless of the structure of this delta and sigma. In fact, in the paper, we have shown that under certain conditions, as long as you can ratio consistently estimate those two norms, in fact, we can, then regardless of the structure, the Bootstrap distribution will be asymptotically the same as the true distribution. This is also known as the Bootstrap consistency, but for the sake of time, I'm going to skip the details here. Okay. So here are some simulation results. I'm going to skip this part. This is basically a point estimation comparison. Compare our method with the least square counterpart. And the overall solution would be our method is preferred because of smaller mean square error, more robust to heavy tail data, and certain advantage for large P sub 1 case. Okay, I'm going to talk about this confidence interval comparison first. This is the DDP would be very similar to our testing simulation. For the sake of space, I'm going to present this banded covariance here. Okay, we generate data from multivariate normal, from heavy tail distribution, and we selected the case where this chain point is at the 20% of the data, it's near the boundary. Okay, and we generate delta randomly, and we normalize it to 2.5 to control the overall signal strength. Okay, we have 7 different confidence intervals here. The first 2 are based on asymptotic distribution. The difference would be the first one is based on AN, which is oracle. We don't know AN, okay, but we use that as the rate of convergence. The second one is using a ratio consistent estimate of AN hat. Okay, 3, 4, and 5 are 3 confidence intervals based on Bootstrap. The difference is that for confidence interval 3, we use the difference between the pre-break sample mean and post-break sample mean to estimate delta. 4 is the one we introduced, the parametric Bootstrap. The 5th one is a non-parametric Bootstrap. Once you have the chaining point location, you randomly shuffle the data in the pre-break sample and post-break sample. By using this, you create Bootstrap data, and that's number 5. 6 and 7 are 2 confidence intervals based on least square estimator. 6 is based on asymptotic distribution, and 7 is a Bootstrap confidence interval. Okay, and here are the results. We use different colors to differentiate different method here. U1 and U2 and LS1 are 3 confidence intervals based on asymptotic distribution. Well, you can see probably because of some misspecification issue, they do not have some accurate coverage, especially when P is large. For Bootstrap intervals, overall, we recommend the parametric Bootstrap we just introduced today. Okay, this U4 because of its coverage. For LS2, the coverage is quite good when the sample size is large compared to P. But when N is small compared to P, the coverage is poor. So again, it shows that we have an advantage for high dimensional data by using the U-statistics framework. Okay. Let's revisit our real data illustration here. We cannot directly apply our method because we are doing a single chain point model. But at the first stage, we can try to use some multiple chain point method to give some initial guess for those chain points. And then we select those segments that contains only one chain point to collect our confidence intervals. So in total, we have 4 confidence intervals here. And as you can see, the stronger the signal, the smaller the margin of error. The weaker the signal, the larger the uncertainty. So this shows that the confidence interval is more informative than the point estimator. But we have to admit that we are doing post-segmentation. So we do not know what's going to be the effect for the first step to the confidence interval construction. We're going to leave that as one of our future study direction. In total, you can see those confidence intervals come in pairs because they are actually the boundary for those regions. For each region, you get 2 points, right? So you can explain this result very well in this data set. So here are some related work. This one is the paper that first introduced self-normalization in high dimension. Also, it gives us the idea how to use statistics to do inference for time series data. You basically remove the tuples containing the observations that close to each other to remove the serial dependence asymptotically. Okay, using so-called trimmed use statistic. And this paper is the one we talk about adaptive inference based on LQ norm of delta by combining different Qs. So that is a strict extension of the method we are talking about today. So they share the same flavor basically. And here's the conclusion of today's talk. We develop a novel use statistic-based approach. We target at dense alternatives, and we have no distributional assumption. Especially for independent data, we have no constraint on the order of P, and we have no tuning parameters. In the future, we are interested in constructing confidence intervals for multiple changing points simultaneously. We also want to apply the method for, say, for example, to dynamic network data. That is a very interesting type of data. And we would like to do something more general rather than just mean over variance, but say chain points for distributions, for marginal distributions or some other type of distributions. These are some references about the papers I mentioned today. If you're interested in, just send me an email. I definitely can give you the list of all those papers. And this is just a summary of some of my recent works are related to or may not relate to the talk I presented today. All right, that's it. Thank you very much. Welcome to any question.
Thank you, Runmin, for the nice talk. I'll open this up now for any questions.
Hi, very nice talk.
Thank you.
I have a question for your last simulation setting that you showed when you did the non-parametric bootstrap. The coverage was much lower when P was growing.
Mm-hmm.
I was wondering if it's because of the sigma that you were using doing non-parametric bootstrap probably was not taken.
You mean the parametric bootstrap?
No, the non-parametric.
The non-parametric bootstrap.
But it's worse if you didn't
Right.
have the right coverage.
In non-parametric bootstrap, we don't really estimate this sigma. We once you know the chain point location roughly, you randomly shuffle the data. Just randomization. You shuffle the data, you create bootstrap sum. So we don't really estimate anything here.
You shuffle the. Oh, you're on argument side here. I'm just thinking that if you shuffle general, the ordering is not.
Because we are talking about this independent data, and also dimensional-wise, we don't have any restriction on the cross-sectional dependence. So I'm not really sure how, what's going to be the interplay. But I believe one reason that can lead this non-parametric bootstrap fail is that we are still using the sample mean. That is a big problem for high-dimensional problems. The sample mean will be, not consistent to the population mean in this case. So I believe that's probably one of the issue there. But that's a good question. Maybe we can investigate that. But since the parametric bootstrap works, at least satisfactory, so that prevents us to think about more. So yeah, that's about it. Mm-hmm.
The assumption 3 forces control over interaction.
Right.
It's interaction among what?
It's this term, basically this I2 term. We call it interaction. It's not really an interaction between 1 and 2. It's just we call it interaction term, and we just want to make this I2 term asymptotically negligible. It's sort of a technical assumption here, and it's just one of the asymptotic regime. I said that this one is not the required one. When the opposite set happen, that means signal is relatively strong, right? That basically means when the opposite side is happening, basically means this delta is at least at a certain level. Then, right, you can just think about, say, sigma is identity, right? So in this case, this basically means dense and strong signal. So even low dimensional method can detect such signal, and asymptotically we behave almost the same. So I just want to explore this specific asymptotic regime here to show some result here. But I think we have a more comprehensive explanation in the paper. Okay, so I think that is now on archive. So if you are interested, we can discuss that later for sure.
I have one question, but it's quite, it's maybe obtuse. I have problems understanding ordering over cross sections.
Okay, we don't have ordering, to be honest here. So, but we allow to basically, if you have ordering, you can do permutation, but we don't really have any ordering here. The one we have is basically these two assumptions. They are just like a summability assumptions. So if you have ordering here, you have or not doesn't really matter. You just, make sure that, heuristically, the row or column of the sigma should be summable to some extent.
So I kind of get that.
Mhm.
It's weird.
Right, but we just don't have any.
Is it standard kind of, is it sort of a
Now standard,
over time series you can accept it, like as something.
right, serial dependence.
Big kind of dependence declines. But if you have like a longitudinal data, what you're sort of saying is there's really no ordering in there. Either the dependence kind of decay, which requires the ordering, or in some sense, there's
Right.
very big dependence between them. There's no ordering, and then it's really hard to understand.
Right, that is quite natural assumption. If you have ordering, and I believe if you impose certain like geometric decay or polynomial decay, that would be a sufficient assumption to these two. But think about, right, if you collect the stocks for say SP500, you shuffle the data, you really don't have a sort of order there. You just aggregate something simultaneously, like panel data. You don't necessarily have a ordering there up to a permutation, basically.
But you do the asymptotic in the panel.
Yeah. Along the panel and along the temporal, along the time direction, basically two directions to do the symptotics.
For time series data, when there is temporal dependence, does one require a sort of balancing between cross-sectional dependence?
That's a very good question. For dependent data, the assumption would be modified a little bit. There is an interaction, there's an interplay between the cross-sectional dependence, temporal dependence, and the tuning parameter we have to choose to make it asymptotically legible for the bias term. Definitely there's interaction here. They both cannot be too strong at the same time for sure. There's an interaction there, I believe.
I have a couple of questions. One is about your, I guess it's showing up in the first set of simulations also under the testing. So it seemed to me that if your sample size is increasing, okay, for any given p, the results tend to get worse.
Really?
In terms of the power. I mean, I may have missed it. So
You mean this part?
the more disparate the p and n is, the results are better, is what I'm trying to say. Like,
I think for fixed p, the increase n, at least I think the power is getting increased, right?
right, but your type 1 errors are also getting, I'm guessing.
Oh, the type error.
Like with your sample size 500.
Oh,
Type 1 errors are definitely worse. So I'm trying to understand what's the intuition behind it, that you need more disparity between.
not really. I think probably due to some random chance here showing this result. I don't really think the n goes to, the n is larger, the type error can be worse.
Right.
So probably that's because of some random chance, or maybe we run the thing or change another seed. Probably we just solve the problem. But yeah, we don't really observe any theoretical side.
So in general, your theory as well as results should tell me that p and, as long as they are both going to, you are allowing for very probably general regimes in the p n, but as long as they both go to infinity, the results should keep getting better. Right?
Correct. Yes.
Okay. The second thing is, if you need any, so why did you choose not to compare with any kind of sparsity favoring method? Is it because
their method just failed for our setting. I want to provide a more fair comparison. I don't want to show, because for some sparse alternatives based on method L infinity, their convergence rate are really slow. So for such A and P, they may not have accurate side, although their theory shows that they have a quite accurate side. So when we use this setup, they just performs quite badly, and we want to have a quite fair.
But at the same time, your method can apply to sparse settings as well, right?
Yes, regardless. So we just talk about the L2 norm of delta.
Correct.
If delta is sparse, but you have a decent norm, we can still do that. But I believe that is just something I said, strong but dense case. Say, if it's very sparse, but the signal is really strong, even growing at the rate of p, I think any method can do that. So that's a very good question. Our method just target on the L2 norm. We don't really have any sparsity assumption here. But for most of the time, we just talk about, dense and weak signal.
Right. But your consideration of the U statistic has a lot of connection directly to the L2 norm, right? Like
right.
At the very beginning, the motivation that you're talking. So is there any tweak you see there that can actually help us target the L infinity norm?
That's an extremely good question, to be honest, because we have this adaptive test. We have shown this this adaptive paper, we combine different tests for different Q. And for not chain point problem, for 2 sample mean testing problem, when this Q go to infinity, it actually converges to the L infinity norm. So that is a paper shown by Gongjun Xu and his co-authors in Annals of Statistics. But we haven't proved such phenomenon for chain point because that requires a process level, which is essentially more challenging. More than besides the finite dimensional convergence, we also have to show tightness. That makes the whole things very difficult. But we assert that for chain point, it behaves the same. Also, those LQ norms, they are asymptotically independent. So that is the base that why we can combine them together. In fact, that is also one of our current direction. We want to prove sort of, connection between the U statistic and the one for L infinity based method. Thank you.
Are there any other questions? Well, if not, let's thank you.
Thank you very much.